So our warm-up today, I'm going to try, if I do this, no, that doesn't help, it just moves it to the other side. I'm trying to think, there's a way to get these little things just here on the bottom. Probably the little, this thing? There we go, that'll help.
Nice.
Alright, so that I have to reach up so high when I do that. So, thank you, yeah, so, good, thank you. Okay. So, yes, it's warm-up time. We're going to write each fraction as a sum of two or more fractions with unlike denominators. I've just got one or two examples, one for the first two and two for the other, but there are lots of ways to split up these fractions. So who has a way of splitting up 5 6 into the sum of two fractions? Who's got one? Anyone? Yes?
1/3 plus 1/2.
1/3 plus a half, right? Now, how did you figure that out?
So you can split it up into like fractions that you can reduce, so it becomes like 4, or wait, I did it a different way. But one way you can do it is make it into 4 6 and 1 6.
Oh, there you go. Yeah, I think what you did was 2 6 and 3 6.
Yeah.
Reduced?
Yeah, that's what it is.
Yep, yeah, that's what I did. Yep. But yeah, you could do 1 6 and 4 6 and reduce those, right? Is that what you did?
No.
No, okay. But you're with us,
Yeah.
right? Yeah, that's good. Good. All right. Put down the shade. Okay, so yeah, that's that one. All right, so next one, 9/20. Someone tell me what 9, yes, Brian?
1/5 and 1/4.
A fifth and a fourth. Yes.
Hey.
Did you do it a similar way? Do like 4/20ths and 5/20ths?
Yes, that was my thought process.
And then reduced. Very good. Any others? 1/20th plus 2/5. I know I saw at least one other person with that one, right? Fantastic. Ooh, the hands are up. Yeah, a lot of people agree. All right. Any others?
What were the ones I already called?
1/20th and 2/5, and 1/4 and 1/5. Okay. 3/10 and 3/20, right? Yeah, 3 and 6. Yeah, beautiful. Yep. All right, fantastic. I just have one of those. I did the 1/4 and I did 13/15. Yeah.
2/3 plus 1/5.
2/3 plus 1/5. Any others?
That's what I had.
That's what you had? 1/15 plus 4/5. Yes.
3/5 and 4/15.
3/5 and 4/15. Whoa, you're matching Brian problem. That's good. All right. I think I have a couple of them on here, but there's more, right? Okay. All right. Good. So the main thing that we're trying to point out to you in this little exercise is that if you take a fraction, you can split it into a sum of two other fractions, right? And the denominators often will multiply to give you the denominator of the original fraction. Does everyone kind of see that? So like here, we have 9/20, we have 4 times 5, right? Here, we have 13/15, and then we have thirds, and that one doesn't work, but this one does. Anyway, yeah. So yeah, I think that's why I did that one, because I was starting to think, oh no, I want to multiply. So anyway, yeah. So you can always, not always, but you can take a fraction and often split it into a sum of fractions where denominators multiply. All right. It really only works well though if the denominator is not prime, right? Factorable. Okay, good. Oh, that's another homework question. All right, so today we're going to learn partial fractions. This is section 8.5 part A. Tomorrow we're going to do 8.5 part B. Right? Okay. So tomorrow's just a continuation of today. It's doing partial fractions, if I remember right, with I think some definite integrals and maybe a few other little things, but it's a lot of review of what we're doing today. So really kind of spending 2 days on this topic. Wednesday, we jump back to chapter 6 and we learn how to integrate logistic functions. And once we do that, we're pretty much done with just about all major integration methods, right? Yes?
Okay, I don't know if you might know this, but for like Calc 3 and like on, will there be any like more different types of integrals?
Probably, but the thing is, Calc 3 is multivariable, so I think it's going back and doing a lot of what we've done with multivariable functions, where you have multiple, like f of x comma y, you have multiple inputs. So it's a whole new ball of wax. Right? We got a lot of new balls of wax. No. I mean, that doesn't mean that I wouldn't ever, but I have never, so. So, yeah. They, I mean, this is,
either that
so
or no
like,
math.
I don't wanna jump like way beyond steps, baby steps. Yeah, we take baby steps. Okay, so anyway, yeah, but the reason I'm telling you that is because then after that, we jump back to chapter 8. 8.6 is integration using tables, which is like a free day basically, where we just use the tables in the back of the book to do all the integrals. It's something that you will never ever actually get to use on anything, right? But it's just so you know they exist, and you know, that's about it. Right? It's like a free day with integrals using tables. It's like using the cheat sheets for integrals, right? So we're going to do that for a day. Then we jump to limits, right? So we back step, really big step back to chapter 1 limits, although it's in chapter 8 because we're learning L'Hopital. And then after that, we do improper integrals, which is really just integrals with limits. And then we're done with the unit. Then review, test. Right? So we will be done with the new material for the unit, I think like sometime middle of next week. We're done with all the material. And then we'll have a couple of review days, and then the test will probably be the following week. So maybe either 2 weeks from today or 2 weeks from Wednesday. I think it's 2 weeks from today. I have to look at the calendar. So you can look at the calendar. All right. Oh, you know what? And there's no school on Monday. So that might be why it's 2 weeks.
Wait, hold on, why is there no school on Monday?
Yeah, I have school, you guys don't have school. It's President's Day.
Summer break? Respect my what?
It's not summer break. Okay.
Both hands. Looks like that.
I respect
All
my.
right. Okay, so let's jump in with partial fractions. So I had this as my original warm-up for today. I'm not going to make you do it. What I'm going to do instead is I'm going to kind of just slowly walk you through how it would have been done had I forced you to do it. But what I want you to do before I start is I want you to tell me how you would start this problem if it was presented to you.
You'd factor the denominator.
You would factor the denominator. You will do that if we're doing partial fraction decomposition, which is what we're learning today, right? Which is fantastic. But you haven't learned it yet, so there's another way to do it. Yes? You would complete the square. So when you complete the square, what makes it extra fun on this problem is that the middle term is odd, so you get fractions, right, when you complete the square. Okay, so now we complete, the other thing that makes it fun is you end up with an x term that's squared. Instead of a quantity squared plus a number, you have a quantity squared minus a number, which means it's not an arctangent, so you can't just jump to arctangent. So now you've completed the square, you have this lovely quantity squared minus a number, and you're looking at it and you're like, well, what do I do now, right? Use some won't work. Completing the square, I don't know what that helped you with. So what did we just finish learning?
The triangle.
Right, we call that trig substitution. But trig substitution really only applies if you have a square root of a quadratic, right? Could we turn the problem into a square root of a quadratic? Yes, yes. Okay, I'm just trying to remember names. Yes.
You take the square root and then square it.
There you go. Take the square root and square it, right? So, great minds think alike because That's what I did, right? So I took the integral, completed the square, and then took the square root and squared it. Now I can apply some trig substitution. So I drew a triangle, and this term, right, first term squared becomes your hypotenuse. Put the number on the bottom, put the root on the other side, and then start solving for trig functions, right? So the first thing I do is I identify my root. So my root was equal to 1/2 tan. Then I identified my x variable, so x minus 5/2 is 1/2 secant, solved for x, and then found dx, right? Which I did not forget the d theta, right there. Okay. Alright. So then it was just a matter of substituting everything back into the original integral. So we've got this beautiful integral, went ahead and divided 1/2 by 1/4 and got 2. And we have a secant tan over tan squared, so you can cancel a tangent. Right? Secant over tangent actually simplifies to 1 over sine, so you end up with 2 cosecant. So our integral then is -2 natural log cosecant plus cotangent. Are we done?
No.
No, why not?
Of course not.
Because we need to do that thing where we can.
Gotta plug the x's. We gotta replace our thetas with x's, right? Okay, so I go back up here and I say, well, let's see, I need a cosecant and a cotangent. So cosecant, well, cosecant is hypotenuse over opposite. So it's the x minus 5/2 over this root. Cotangent is adjacent or opposite, so it's 1/2 over this root. So we plug in the x values and we get that.
Oh my god.
Now the problem said to simplify completely, right?
It's the same
You
number.
can! Yes, you can just add it, right?
the same
They're
thing
like
on the bottom.
denominators.
Yeah.
So when you combine, you actually just end up with an x minus 2 over the denominator, right? So we've got an x minus 2 now over the denominator. What I did was I rewrote the denominator back into its original quadratic form and then factored. Factored, yeah, I factored it, right? Okay, so I factored it. The reason I factored it,
Oh geez.
what?
I never keep going.
Okay, okay.
I get it.
Oh,
I just had
okay.
to bring one.
So anyway, so I factored it. The reason I factored it is because, of course, we can break up the log, right? So now we've got a natural log of x minus 2 minus a natural log, this would be to the 1/2, so you put the half out front, right? And then minus a natural log of x minus 3 also to the 1/2, the half out front. So you end up with that. And then I noticed, hey, we've got a couple like terms here, right? Natural logs of absolute values of x minus 2, so I combined them. And finally, distribute the -2 with the 1/2, and there's our answer. Is that not beautiful? Isn't that nice? I know. The math is beautiful. I agree. Yeah, that's right. So good. So it's a beautiful, beautiful problem. It takes a little bit of time, right? And there's a little bit of room for error here or there, right? Because it gets a little messy. So if you are writing in any kind of a messy way, you might have a few little stray errors here or there. So it can lead to a few problems. Wouldn't it be great if there was a better way?
Yes.
All right, so we're about to learn how to apply partial fractions. When can we use partial fractions? Coldman says we can use partial fractions whenever you have a denominator that can be factored. All right? That doesn't mean that you always want to do partial fractions when you can factor a denominator, because obviously if it's just like a simple u substitution or something like that, then you just want to do it, right? But if you have, 1 over a quadratic and it factors nicely and there's no other real simple way to do it, partial fractions is a nice way to approach the problem, because it breaks it up. So you can use it anytime you have a denominator that can be factored. That doesn't mean you should, but a lot of times it makes the problem nicer. All right. What are we missing from this otherwise Las Vegas type theatrical review? Steps, right? So, steps for decomposing P of x over Q of x into partial fractions. First step that you always want to do is make sure that the degree of the denominator is bigger. If the degree of the denominator is less than the numerator, if the numerator is bigger, the first thing you have to do, what do we do when the numerator is bigger? Long division, right? You do your long division first, then once you've done that, you'll be left with something where the degree of the denominator will be bigger, and then you can apply partial fractions. Okay, next step, factor the denominator completely. Once you've done that, you're going to break it down into sums of fractions. Sometimes all the denominators will be linear. Sometimes they'll be a combination of linear and quadratic. You can use partial fractions even with cubic or quartic or quintic, right? But no one's going to make you. It will always be linear or quadratic in this class. And on the AP exam, it'll always be linear or quadratic. Okay. So, break down linear factors. There must be as many fractions as the degree of each factor. It's kind of weird. I'll show you. It's easier than it sounds. Alright, so for linear factors, numerators are always constants. For quadratics, the numerators are all linear. For cubics, the numerators would all be quadratic. For quartics, the numerators would all be cubic. In general, the numerators will always be 1 degree less than the denominator. There's an exception to that, though. But it's really not an exception. It looks like an exception, but it's not. It's a deceiving non-exception. So I'll show you that. All right. I don't know if I want to leave that up or rewrite it. I think I'm going to rewrite it. So going to erase.
Miss Price,
Yes.
real quick, could you go back to those rules? I just want to take a picture so I can write it down.
That's a good idea.
Yep.
You know these are posted on the website too.
Yeah, but it's too difficult to go on the computer and find it.
Yeah, Brian.
Yeah, well.
Brian.
Everyone got it?
We are too.
This really doesn't teach it well. You really have to work through the problems to know what to do. Okay. All right. Good. All right. So here we go. We're going to do the same problem we just did a minute ago, using partial fractions. So the first thing we're going to do, we're not going to do the integral. We're just going to find the partial fraction decomposition for this function. So the first thing you do is check the degree. The top is lower than the bottom. We're good. Next thing you do is factor the bottom. Remember, take second and factor the denominator.
There's a highlighter next to the actual marker. Yeah, I don't know.
That's,
I was
I
saying
think
that's
we
really
know.
good.
Dangerous
Yeah,
right
that's why I
there.
was like, good.
Somebody's living on the edge.
Okay. Did y'all get that? It's worth your time to take the 10 seconds and at least mentally multiply it back out and make sure that you factored it properly, because if you didn't, the whole thing's just going to be a mess. So make sure that you didn't accidentally drop a negative or anything like that, that everything's correct and clean. Okay, next what we're going to do is split up the factors. So if you remember from our number examples, what we ended up with was something over each of the factors of the original denominator. When the denominator was 6, we had something over 2 and something over 3, right? There's other ways, but this is how we're going to do it, right? So, same kind of thing here. So this is our denominator, so we have something over each factor. Our job is to figure out what has to go on top to make this equal to that. So we end up with an equation that looks like this. and we have to solve the equation. Does anyone remember how to solve a rational equation? What the first step is? Yeah, so you want to multiply every term by the LCD, and I'm going to move this down a tiny bit and write this small. Just in case you've forgotten how to do this, the LCD for this is x minus 2 times x minus 3. So when you multiply every term, both sides, on the left side, the x minus 2 times x minus 3 is equal to the entire denominator, and the whole thing cancels, and you're just left with 1. For this term, the x minus 2 cancels, so you're left with a times x minus 3. And for this term, the x minus 3 cancels, and you're left with b times x minus 2. So when it's all done, you end up with that. So when you multiply through by the LCD, all the denominators are gone. They all cancel out. Do you all understand how that works? Yes. Good. How do we solve this equation? There are several ways. So I need to reach it up now. All right. So we need to solve for a and b. We have one equation and 3 variables, right? Really one variable, 2 unknown constants. All right, so we're really not solving for variables, we're solving for unknown constants. The nice thing about these equations is that they have to be true for every single value of x, which means we can plug any value of x we want in, and we would have to have a true equation. Can anyone think of a good value of x to plug in? 3, right? Because if we plug in a 3, this term goes to 0, and we just end up with 1 equals b, because 3 minus 2 is 1. We just solved for b. Does that make sense? What would be another good number to plug in?
2.
2, right? You plug in a 2, that term goes to 0, and we're left with 1 equals negative 1 times a, so a is negative 1, right? So you plug in a 2, you get a is negative 1. You plug in a 3, you get b is 1. So then our final equation, 1 over x squared minus 5x plus 6 equals 1 over x minus 3 minus 1 over x minus 2. So you just plug your values for a and b back in. All right. Now, let's think about the ramifications of this. So we already did this. It took us like 10 minutes, right? Now that we know that this equals this, we can just jump right to that same answer. Right? That was the final simplified answer. Yeah. Bam, you're done. Yeah. Isn't that nice? Okay. So really what it does is it takes a polynomial that's any degree as long as it's factorable, right? And breaks it into a bunch of smaller, simpler fractions that you can then just integrate. Yeah, sorry.
Could you go back just to one second?
Yeah. Oh, of course.
It's right. You can't just randomly put numbers in there.
There's just one though, isn't it?
Well, no, not always one.
Oh, it's not? Okay.
It just happens.
Sorry, do you have a
Yeah.
question?
No, we got it.
Yeah.
Alright, okay. So, are you guys ready to try one? Yeah.
You gonna give us a hard one like this?
Like, well,
Alright, so I want you to take a minute. First we check the degrees. Is the top less than the bottom?
sure.
Yes, then we're good. So the next thing, what's the next thing we have to do?
Factor.
Factor. Everybody take a minute and factor the bottom. Top you don't have to factor, it's up, that doesn't really matter. It's the bottom that has to be factored. Alright, everyone got it factored? Yes. Okay, this problem has, whoa, it's this problem has what are called repeated linear factors. That means that you have linear factors that are a quantity raised to a power, right? So the x minus 3 is repeated twice. When you have repeated linear factors, something mildly unusual happens. So you have to write a fraction for each degree of the factor, meaning that there will be a fraction for the x, that's fine, but then there will be two fractions for the x minus 3. It's not exactly how you think. It's not like an x minus 3 and another x minus 3. So the way that it works is you write a fraction for the x, a fraction for the first degree of the x minus 3, and a fraction for the second degree of the x minus 3. If it was cubed, you'd have a fraction for the third degree of the x minus 3. And you would keep going. Hold that thought for 1 second. So you have a fraction starting with a power of 1 that goes up all the way until you hit the highest exponent on your repeated linear factor. You could treat this as a quadratic and use a linear numerator on top instead of a constant, but it makes the problem more difficult. What we've done is actually equivalent. Let me show you why. Can you, Sora, can you make sure that what I'm doing is on the camera? Is it, if I write over here, will it be on the camera?
Yeah. Oh,
Can I just pick it up?
just broken. You got it, Brian. I think we got it.
Yeah, man.
Alright, good. So, if we have b over x minus 3 plus c over x minus 3 squared. What bothers people is they're saying, well, you just said that you have to have a linear over any quadratic factor, right? This is kind of the exception, the non-exception exception. Because if we were to combine these and treat it truly as just one quadratic factor, because it wouldn't be multiple, right? It'd just be one. There's just one quadratic that's, one thing that's squared. Well, if we split it up like this, if we find an LCD, what we would end up with would be b times x minus 3 plus c over x minus 3 squared, which ends up being a linear over a quadratic, right? So we have a linear over the quadratic, it's just that we are writing it in a different way. You can only do this for repeated linear, and you should do it for repeated linear, because it's so much easier than treating it as a quadratic. So you can, if you would prefer to write ax and then just have a bx plus c over an x minus 3 squared, you would be able to solve it and it would be okay. but this is the easier method. It's faster. Faster and simpler. And you'll get used to it with those repeated linears. So constants over any linears, including repeated linear factors. All right, good. So what I want you guys to do is take a minute and I want you to write an equation so that you can find A, B, and C. And your equation really should look like this equals this. Right? Something like that. So you have to multiply through by an LCD and see if you can find some values.
Oh, good question.
No, just two of them. So the LCD for this, would it be x times x minus 3 times x minus 3 squared, or just x times x minus 3 squared?
X times x minus 3 squared.
X times x minus 3 squared. Yes. Times every term. Yep.
I got C equals 5.
Yeah. I got C equals 5.
So check and make sure that your original setup looks right.
Oh, yeah.
Similar? Okay, good. See if you can find A, B, and C.
Find it so you have to find B.
Remember, you can plug any number in for x that you want.
Doesn't have to be real.
Well, you know, it will probably be more helpful if it's
I would go with 5.
You were right about that. What's that? Yeah. That's a really What's 6 divided by 9? What's going on?
Hey, does anyone have an eraser?
It'll make mistakes.
Matt, I'm not perfect like you.
Oh, that's fair. That's not even a shirt. That's a compliment, so I'll take it.
The only person who has to
Yeah,
be
and I was being
is that
sarcastic.
right?
He's probably sick
Yeah, he's
again.
definitely skipping.
Yeah.
That's like every day to try and like make up. He was in physics class and he was literally there for a third maximum. A third of the day. Because he'd skip. Okay, here's what he would do. He'd like skip physics to take an apps test because he had skipped the test.
So, did you all
But then
get
he missed the physics
C is
test.
5
And then he had to make
and
that
A
up
is
and miss the
2/3?
Yeah.
Fantastic. You get B.
No.
Yes.
How do you find B?
Well, let's see, once you've got A and C, right, you plug A and C in, then pick any number for x that you want.
Yeah, B is just 100.
I would advise picking a small, simple number, like 1
100?
or 100. Yeah, you don't have to pick 1.
100.
I was not being serious in any way.
Nice.
Point pi.
Point? No. 10 to the negative 23rd.
Pi has a point.
She said whatever one I want to do, right?
Why don't you try and type that next to
2.
Wait.
I like it.
Wait, you typed it into a calculator, it'll just multiply it, so you can't.
Not if you can paint.
Yeah. True.
Yeah, it'll just
It's
throw
an
an
error,
error.
syntax error.
Yeah, it'll just tell you did it wrong.
Just multiply it. Maybe. Yeah? What'd you get?
Negative 2/3.
What?
Negative 2/3.
Okay.
Dude, I should win a Nobel Prize.
That's so odd. That's so weird. Wait, what happens if you do like 3.8?
Both sides.
Nice Brad.
You want this?
Hey, don't call me
Point,
that.
no, point two.
This.
Do a
So then when you multiply the
problem we're experiencing is
Whoa.
that bias. So do another
the
test.
two sides. Oh, you've got it.
Okay,
See, you've got it, it's that when you're multiplying for the wrong, because then the denominator gets. You guys do both sides, you can just randomly multiply. You gotta do
If you do like a point instead of multiplication symbol, like on the.
Oh, because it probably takes it to
Okay.
5.0.
Oh, I see multiple answers for
That's
me.
really possible, actually, that's good.
We've got 3 different ones, the ladies I think have 3.
That's a good sign.
Yeah, 3.
You guys have, yeah, tell us.
Never do that again.
Yours. You got, you don't know. I think it's it normally is.
No, I
All right.
Go,
So,
go.
gentlemen,
Just
did
what
any
you
of you
got.
have negative 2/3?
Yup.
Yeah.
Negative 2/3.
Hey,
Negative 2/3.
Yes.
Okay.
8/3.
All right,
Good
good.
answer.
No, 8/3 is wrong.
5, please. Once you find your A, B, and C, you have to plug them back into your integral, and then you still have to integrate, right? All right, but it's not a crazy integral anymore. So now,
Wait.
you've got, you're just replacing, remember this equals
I don't understand how.
A, B, C, plug them in, right? Are you stuck? Can you come over? So
I just
everyone take a minute and find the integral.
I just don't understand how the 3x plus 6 just like magically goes away.
How the 3x plus 6 magically went away? It didn't go away. We used it the whole time we were solving the equation.
We just
Where's your, let me see your.
rewrote it, so it's not. No, like I have all the correct answers, but like.
Yeah. Your 3x plus 6 over this equals something. You used it the whole time you were solving for A, B, and C. So this whole fraction equals whatever you got,
Oh, okay.
right?
Yeah, okay, that
You
makes
have a
sense.
natural log of a square. Can you bring the square out somehow, some way?
Yeah, yeah, absolutely.
So,
But you can't, that is not a natural log of a square. Natural log only works when you have a linear denominator. Everything else has to use what?
U rule. Power rule. Power rule again. Crap.
Well, anything to the negative second, integral, add 1, divide by the power.
Do you need a U for that, right? No?
I would find it next.
So is it 2/3
I'm
natural
blanking.
log of
Sorry.
First one's natural.
First one is a natural log.
Minus 2/3
First four natural logs.
Minus
Last
2/3
one.
natural log of
Okay.
x minus 3.
plus
5.
5.
All right, so I'm hearing some discomfort with the third
Yeah,
term.
5/3.
No, minus 5.
Yeah.
Would you minus 5?
So the first term, natural log. Any questions on that one? Second term, natural log.
Minus
Any
5.
questions on that one?
Oh, yeah.
Is the third term a natural, oh, yes, please.
I pulled out a 5.
You sure? Okay.
Halfway there.
Write down.
There.
Is the third term a natural log?
No.
No. Natural log is not the integral of 1 over anything. If it was, we could just like have 1 over anything and put natural log around it and be done, right? Wouldn't it be nice? I know. Okay, so, quiet. So instead, but this is, remember, it's just x minus 3, so it's just a linear factor raised to a power, it's powerful, right? It's 5 times the quantity x minus 3 to the negative second, raise the power by 1, divide by the power, and you end up with just negative 5 over x minus 3.
Solid.
So it's just a straight up power rule.
Come on, guys.
Okay, let's try another one.
I have a question.
Yes.
So if it says to, I mean, if it says to factor, like, simplify completely, would you have to, you're gonna have like, let's say that, x over x minus
Like,
3.
why would I need to find the area under the curve for y?
Would you?
If that actually came up in physics, I was like, yeah, finally.
That's like
Probably
the
be
most
a
basic
multiple,
thing.
probably.
Like it's like the velocity equation.
You could literally count
the
those
squares.
Alright.
Yeah.
Like, how are we gonna get a situation
check
like
that
this
out.
where it's like this is his position and I have to take the or his velocity and I have to take the integral.
I can't wait to finish this class and after the AP test, never do this again.
Yeah, except for in college.
And
Calc 3, yeah. Are you taking Calc 3 soon? Alright, fine boys, okay.
Are you?
I'm gonna do it.
Why?
I don't
4K.
So I was gonna say business or engineering, but I end up hating math now.
Lot of those in the camera.
Personally, I'm going into engineering because, well,
Where do you want to go, Brian?
my dream school's MIT.
Quiet. When you have a factor that is quadratic, and it can't be reduced, right? It's just, you're stuck with a quadratic, right? So when you have a factor that's quadratic, then you put a linear numerator above it. The linear numerator has to be of the form mx plus b kind of a thing, right? So people were annoyed earlier today. They wanted to just, for this one, just have cx with no plus d there. But there has to be a plus d, because you can't assume that the y-intercept of the line is 0, right? It could be anything. So you treat it just like any other linear equation. It's an ax plus b, in this case cx plus d, say they are used. But anyway, so for your linears, remember any linear factors get constants on top. Quadratic factors get linear equations on top. So I want you to take a second and see if you can solve this one all the way through, including C and D. Oh my gosh, guys, we've just started too. So let's not groan yet, because.
Jeez, Brian.
Well, we won't be doing this for calc. Hey, don't touch my shoes, don't touch my shoes.
He made Jake got him dressed shower. He was getting dressed up. He made Jake get back dressed for practice.